Hello, everyone, and welcome to Chapter 7, Section 2, where we'll talk briefly about ionic bonds and ionic compounds. So here we are last week, or for Chapter 7, Section 1, we talked about what an ion is, and now we're going to talk about how they come together, bond together, and create compounds. All right, so what is an ionic bond? It's a compound composed of cations and anions. And if you need to review what a cation and an anion is, please watch the 7.1 video. Although ionic compounds are composed of ions, the compound itself is electrically neutral. What is an ionic bond? An ionic bond is an electrostatic force that holds oppositely charged particles together in a compound. So a compound is made up of cations with their positive charge, anions with their negative charge. That's what an ionic compound is. An ionic bond is what's holding those oppositely charged particles together in that compound. It's usually a bond between a metal and a nonmetal, and metals will transfer valence electrons to the nonmetal. There's 3 steps in the process of ionic bond formation. So first we form the positively charged ion with a positive charge, and then we form the negatively charged ion with the negative charge. And then we will form the ionic bond. So here we have sodium chloride coming together, sodium with its positive charge, chlorine with its negative charge. When we combine them together, we'll form an ionic bond called sodium chloride, and that is table salt. So let's do an example of sodium and fluorine, for example. So here we have sodium with its positive charge and fluorine with its negative charge. If we look at the valence electrons, we'll see that sodium is going to donate its electron to fluorine to form the ionic bond. So this is the attraction between the positive and negatively charged ions forming the ionic bond. Again, sodium will donate its electron so that fluorine has the octet, the 2, 4, 6, 8 electrons in its valence shell, in those valence electrons. Formula units. So a chemical formula shows the number of atoms of each element in the smallest representative unit of a substance. Ionic compounds do not exist as discrete units, but as collections of positively charged and negatively charged ions arranged in repeating patterns. So for example, we have structures of sodium ion and chloride ion, and then we can see how the arrangement of sodium ions and chlorine ions in a crystal of sodium chloride, then those are all stacked together in repeated patterns to form the crystals of sodium chloride, which are the salt crystals. The chemical formula of an ionic compound refers to a ratio known as the formula unit, and a formula unit is the lowest whole number ratio of ions in an ionic compound. So for example, for sodium chloride, the lowest whole number ratio of ions is 1:1, where you have 1 sodium ion to each 1 chlorine ion. The formula unit for sodium chloride then is NaCl. Although ionic charges are used to derive the correct formula, they are not shown when you write the formula unit of the compound. So you'll notice, the sodium ion by itself will have a positive charge to it, and the chloride ion by itself will have a negative charge to it. But when we combine them together and actually write the formula unit, we do not use any of their ionic charges. So let's go back to the example of sodium and fluorine. The smallest, again, the formula unit is the smallest whole number ratio between the cations and anions in an ionic compound. So here we have the sodium and fluorine. We'll see how sodium, again, is going to donate 1 electron to fluorine. So we get a octet, as you can see here, and you can see how both compounds now have this stable octet in their second energy level, because you can see how they each now have 8 electrons in their valence shell. So this is how we'll write sodium fluorine. You have 1 sodium ion and 1 fluorine ion in the ionic bond between sodium and fluorine fluorine. So this is how you would write the formula unit, NaF, sodium fluorine. Let's go through another example of magnesium and bromine. So here we have magnesium shown here. And bromine, we can see how we're going to have to work with two bromine atoms here. The formula unit will be magnesium bromide because we'll have two bromines that magnesium can donate an electron to. So you'll see that it's going to donate this electron to this bromine atom and this electron to this bromine atom in order to make the stable octet in that valence shell of electrons in bromine. So 1, 2, 3, 4, 5, 6, 7, and now 8. And we have a stable octet now in this bromine. And we'll have a stable octet, meaning we'll have 8 electrons in the highest energy level in the valence shell in this bromine now when it receives an electron from magnesium. Magnesium is a 2+ positively charged ion, so it will donate an electron to one bromine, an electron to another bromine. So the formula unit will be MgBr2. It's able to donate those 2 electrons to 2 bromines. And this is so that now all 3 atoms have a stable octet, 8 electrons in their valence shell. So you have one magnesium ion with a charge of 2+ and 2 bromine ions in the ionic bond between them will be the ionic bond between the magnesium and bromine. Example 3, let's look at aluminum and oxygen. So to create aluminum oxide, here we have the formula unit. One aluminum will donate 3 electrons, but there will be 2 of them for a total of 6 electrons being donated from these 2 aluminums. So these 2 aluminums are donating 3 electrons each in order to fill up these 3 oxygen valence shells of electrons. So you can see here how we'll have 2 aluminums donating their 3 electrons each, and 3 oxygens receiving those 6 electrons total. So you can see how we've created aluminum oxide, and the formula unit would be Al2, oxygen 3. You have 2 aluminum ions and 3 oxygen ions in the ionic bond between aluminum and oxygen. Properties of ionic compounds. Most ionic compounds are crystalline solids at room temperature, and the component ions in such crystals are arranged in repeating 3-dimensional patterns called crystal lattices. The beauty of crystalline solids comes from their very orderly arrangement of their component ions. So we can see fluorite, calcium fluoride, and grossularite, which would be calcium, aluminum, silicon, and oxygen. So you get kind of this really pretty crystal structure because of how their components are arranged in these 3-dimensional crystal lattices. More properties of ionic compounds. Each ion is attracted strongly to each of its neighbors, and repulsions are minimized. So the large attractive forces result in a very stable structure. And we can see that in these ionic compound structures here. A very stable structure because each ion is strongly attracted to their neighbors and repulsions are minimized. A unit cell is the simplest repeating unit of a crystal lattice, and the coordination number of an ion is the number of ions of opposite charge that surround the ion in the crystal. So for example, in sodium chloride, each ion has a coordination number of 6. So it's the number of ions of opposite charge that surround the ion in the crystal. So that just means that one sodium ion is surrounded by 6 chloride ions, and one chloride ion is surrounded by 6 sodium ions. So that coordination number is the number of ions of opposite charge that are surrounding the ion in the crystal. So we have this really pretty then crystal lattice structure as shown here. Oh, let's just go back. Where you see one chloride atom surrounded by 6 purple sodiums, and each purple sodium is surrounded by 6 chloride atoms. So we get a really pretty crystallized structure. In cesium chloride, for example, CsCl, each ion has a coordination number of 8, so that one cesium is surrounded by 8 chloride ions, as shown in this picture, and one chloride ion is surrounded by 8 cesium ions. So that is what the coordination number refers to. In titanium dioxide or rutile, this forms a tetragonal crystal. The coordination number for the cation, which is titanium, is 6. So you'll see these gray titaniums, and you should see 6 oxygens surrounding each of those. Each titanium ion is surrounded by 6 oxygen ions, and the coordination number for the anion oxygen is 3. So for each red oxygen, you'll see 3 titaniums surrounding it. So they can be different, coordinations numbers can be different in different compounds. Hard, brittle, and rigid solids. So due to strong attractive forces that hold the ions in place, we get very hard, brittle, and rigid solids in ionic compounds. And a force strong enough to break ions apart will crack or separate the solid where the unit cells are incomplete, usually around the edges of the crystal. Oops, sorry about this. More properties, we have very high melting points and very high boiling points, meaning that you need a very high temperature to melt these ionic compounds and a very high temperature to boil them. And this is due again to the very strong attractions between the positive and negative ions. It takes a lot of energy to melt an ionic crystal or to boil an ionic compound when dissolved in water. More properties, they're soluble in water, so they can dissolve easily, just as if you were to put table salt in water. They can conduct electricity, but only in molten or aqueous states due to freely moving charges and due to electrolytes. Ionic compounds whose aqueous solution conducts an electric current, and why? We'll talk about that now. When dissolved in water, the positive and negative ions can dissociate, that means they separate, from one another, allowing for that free flow of negative charge. So we kind of have an electrical aspect when these ionic compounds are dissolved in an aqueous solution. So that brings us to the end of section 7.2. Thank you for listening, guys, and God bless your